Welcome to the January 2022 webinar. Today we're going to talk about the Australian Water Balance Model, otherwise known as the AWBM model that is implemented in GoldSim. This model has been around quite a while. When I say this model, I mean the implementation in GoldSim has been around quite a while, probably since about 2010. And we've made various changes to it over the years. More recently, in the last couple of years, we've made some changes to it to incorporate some features that have been developed in the software itself. But as far as the main functionality, nothing has really changed. However, more recently, we've made some fundamental changes to the way that the storage is updated and withdrawals are made from them. It doesn't, you won't see a difference necessarily in the results, except that we've provided some ways to work around some time stepping issues. And that's what I want to bring up. So depending on the situation, there could be quite a bit of difference in the functionality, mainly in models that have unscheduled time steps. So that's going to be the focus today, is to talk about that, how the model works, so you can have an idea and what to expect if you were to incorporate this into a larger model, especially that one that will generate unscheduled time steps as you walk through time. I'll walk through that, but what I will not do during this presentation is demonstrate the model in a larger model, but what you'll see today should help you in the process of doing that. Already I'm starting to see that it would probably be nice to have another webinar in the near future in which we focus more on demonstrating how this model is incorporated into a larger model, and also calibration. So that's coming up, so stay tuned for that. But what I want to focus on this in this webinar is mainly just an introduction to the model so you understand what it is, and then talk about the changes that we've made to it. That will be most of it. I'll talk about some limitations and things to watch out for if you're going to use it yourself. And then I also want to talk about where we plan to go with this model going forward. Okay, it turns out that this model is among the most popular of our models in our library. It's got the most downloads and the most views. Just behind the weather generator, we have a stochastic weather generator called WGen. So that one is in first place, and this one is the second most used model. So it's probably a good one to look at if you haven't seen it yet. Okay, so introduction to the model. The AWBM model is a conceptual lumped model that calculates rainfall runoff, and it uses some features that you might see also not exactly the same functionality that you would find in other tools, but it produces similar responses that you might see in, for example, the USDA SCS curve number method. And what you'll see in this model is that we use storage elements and runoff or overflow from those elements, and then use a recession functionality to further develop the components of runoff that allow you to calibrate it to actual observed flows. So let me just walk through the basics here. You see there's this diagram, And this shows the conceptual part of the functionality of the model. So the first thing that we do is we get precipitation and potential evapotranspiration as an input. So typically this would come in as a time series. That's the way the model is set up, is to accept a time series with daily values. If you have something other than that, the model can be adjusted to have a different type of inflow. So for example, instead of a time series, you might have um, an output from a different part of your model. Let's say, for example, you wanted to generate stochastic precipitation values on the fly as you're going through the simulation. This model, the AWBM model in GoldSim, could accept that as an input as well. So it doesn't have to be a time series, but that's the way that it's set up currently, but could easily be changed. The point is, however, is that it is expecting your precipitation values to be daily. If you want to change the model to work on an hourly basis, that can also be done. The concepts are the same, regardless of the specific time step that you want to use in your model. Somebody said it's called Australian WBM. Can you speak to the options possibility limits of using this model structure in the continental US? Yeah, that's a good point. And when I get into the surface stores, I can talk about that certainly. You're right, it is called Australian because the parameters, some of the parameters that are used, mainly the A values in the surface stores, were calibrated for many sites in Australia. Yeah. Okay, so let's talk about that. The surface stores, that's the next part. So the surface stores is the part of the diagram that you see here with the C1, A1, C2, etc. The Australian water balance model is set up with 3 surface stores. Think of them as essentially just buckets in which rain will fall into and fill these buckets. They all have different sizes, and when I say sizes, what that means is they are proportioned with the factor of A1, A2, and A3. And again, there are 3 buckets. They don't have to be 3. You could have uh, more or less than 3, but the model has been developed using these 3 surface stores because it was found that using more than 3 made it more difficult to calibrate, because that means that the calibration factors are increasing, and therefore the effectiveness of those calibration factors goes down if you add more of them. So 3 was found to work well, and also this model has been used because these factors were developed in Australia. Um, they're, the climate of that area needs to be taken into consideration. If you're going to use the AWBM model in an area with perhaps a very different climate than in Australia, then it may be more difficult to calibrate. What we have found so far is that if this model is used in areas that are arid, that it will work nicely even outside of Australia. What I would suggest doing is playing with this model and seeing how the calibration works. And we'll talk about calibration a little bit later, but let me describe the surface stores for you so you can understand how they work. We have three surface stores in the model, and they are proportioned by default with the A factor. And so it's set up currently with these three different A factors, and they are proportional factors, meaning that they are intended to divide your catchment up into three areas, in which each of these three areas have different capacity values, capacity C1, C2, and C3. And they are proportional factors, so each of the A values must add up to 1. And so it's just a way to divide your catchment area into three different proportions. And so you have the ability to change A1 and A2, and then A3 will just be the remainder that adds up to 1. So the A1 and A2 must be a value between 0 and 1. Okay, so for example, if you made A1 and A2 a 0.5, each of those 0.5, then A3 would be 0. So you'd really end up with just two proportions. Okay, so then you also have the ability to change the capacity value for each of those. Now, the A values are not intended to be calibration inputs. Rather, they are intended to be left alone, unless you find that for your sites that you should have some other area proportion values. But currently they are set up to be constants and not adjusted. Instead, to calibrate your model, you can adjust the capacity values. And there are ways to figure out what type of capacity values to use in your model, depending on monthly rainfall excess that you calculate, and comparing that to your precip and your uh, observed runoff. So I'll talk about that again in later when I get in more into calibration. Okay, so the way that this works is rainfall fills these three buckets, and when overflow occurs, that becomes rainfall excess and contributes directly to runoff. What we do, however, is we also remove the potential ET as these buckets are filling. Because the buckets are different sizes, then each one will begin to overflow at different times. Okay, so once we calculate the rainfall excess or the overflow from these buckets, we add them up and then we split them in two different directions. In one stream, it goes to surface runoff, which is another store, and then the remainder will flow to base flow, which is also a store. And each of these stores then have a recession outflow. So think of it as a small hole in the in a tank, and you fill this tank, and the outflow is a function of how much water is in that tank currently, and it's using a recession constant to deliver water out of that tank and contribute to runoff. So again, why are there three surface stores? It was really just found that this provides the highest amount of flexibility to fit the rainfall and runoff data for doing calibration. Using less than three made it more difficult to fit to make the model robust, but more than three made it difficult to provide calibration. So that's why there are three. Again, A1, A2, and A3 represent proportions of the catchment that you can divide it up into. So maybe if you have parts of the catchment that that do not have a lot of capacity to absorb moisture when it rains, then that area of the catchment would be represented in A1. If you have other parts of the catchment with soil that can accept a lot more moisture before running off, then that would be represented as a different, larger part of the surface store, or a surface store with a larger capacity. such as C2 or C3. So those values, C1, C2, and C3, these are depth capacities assigned to each of those three proportions. And any excess rain above those capacities is then calculated as overflow and contributes to runoff. Okay, so there, like I said, the runoff, the overflow from those surface stores is then diverted to one of two places: surface flow or base flow. Actually, I said that wrong. Surface runoff or base flow runoff is the terminology they use. Okay, so the surface runoff will have a smaller recession constant being used, which causes the outflow from the surface runoff store to be more, to have much higher spikes and quickly dissipate. So there's little attenuation there in the surface runoff. That's what you should expect to see. If you look at the graph on the right, you'll see that we have the two components of our runoff being the surface runoff and the base flow runoff. And you can see that the red line is showing a value that is not slowly attenuating, but has higher spikes and more closely related to the excess rainfall. Conversely, if you look at the base flow component, or the overflow from the surface stores that contributes to the base flow runoff, you will see that in this case we use a much higher K value, much closer to 1, with a higher recession constant of K. Then you can see that the tail, or the discharge after the rain occurs, is much more gradual and has a much longer recession flow. So by dividing the runoff into these two components, it allows you to have a better grasp on how to calibrate the model. So if your spikes are not high enough, then you can adjust the amount of overflow that contributes to the surface runoff. Or if you are showing greater spikes and more spikes in your simulated flows and are not able to match the observed runoff because of that, then it would indicate that you could contribute more of the overflow to base flow runoff instead of surface runoff. So you have those factors that you can use to divert the water to one or the other. And if I go back to the diagram, then you see there's this split that occurs after the surface stores, and that split is done using a factor called the BFI factor. So you can increase that factor to increase flows to base flow, or decrease the factor to increase flows to surface runoff, depending on what you see in your observed record. Okay, so somebody's asking, can you put precipitation on that graph to see how that is delayed? Yes, I can show that in the model itself, which I will go to is after I, well, I could probably just do that now. So let me go into the model, and let's just run this model for a year so we can see what that looks like. Okay, and so the chart where we look at the components of the runoff is located in here. So if I open up that chart, here is the surface runoff versus the base flow runoff in blue, and then the combined runoff is the black dashed line. So now we can add precip to that. And I should maybe put this, let's see if that helps. Y2 axis, not reversed. Well, maybe reversed is better. There's too many lines. Okay, so the precip is this magenta line that is in a reversed, well, I'm just trying to think of a better color. There's not a great color for it, but let me just zoom into a spot here. So you can see precip occurs on February 21st, and that contributes to a spike in runoff on the next day. And then if I zoom out, then you can see the impact there. But typically the surface runoff will be a pretty immediate reaction to the precip, and then the base flow contribution will be much more delayed because of the recession constants that we're using. So there you have it. All right, continuing on. Okay, let's talk about updates to the model. So the updates that we've made in the last year or two have been mainly to add the features that we've been putting into GoldSim since then, mainly being that we can embed a time history chart. Well, you can now embed any result element in your dashboard, and that's what we've added here to our dashboard. So you can see the charts right in the dashboard embedded. You can double click on those charts to expand them. But we've also added the simulation start and end date in the dashboard, and that's seen in the upper left corner. This is a control that allows you to control the simulation start and end date directly from the dashboard. It's just a little bit of a convenience, but doesn't really change the model at all. We also provided input fields for initial store values. The initial store value is just the value that the stores have at the beginning of the simulation. This is important if your model is of a system that starts with some antecedent moisture in the soil. So at the very beginning of the simulation, when it starts, is the soil dry, or is there still some leftover from a previous storm in the soil? And if there is, then you'll want to put those initial states there. For the surface stores, instead of defining an initial value for each of those 3 stores, instead we thought it would be easier to just specify a % of capacity as one number that might be easier than defining 3 different values for the surface stores. So you can just specify it as a %. What's the % of the total capacity as far as the starting point of the moisture condition in the surface stores? So that will help with calibration, particularly if you've got some sort of starting value in which your soil has some moisture in it already. Okay, the run button that's shown at the bottom left corner of the model, when you click run after the model runs, then it changes to reset. You click on that and that will reset the model. We also have default values set up in all of these inputs. So you can click a button at the top that says reset inputs, and that just changes everything to default. And now the default is set up to be inputs that are used in another tool so that you can do a comparison and validate the model before you use it. So that leads to another topic of how we have added some validation to the model. The validation that we added to the model does 2 things. One, it checks to make sure that the GoldSim output matches the output of another tool that we looked at. And by the way, yesterday it was brought to my attention that some of these values that are shown here on this slide need to be updated. The K values are not correct there. So sorry about that. I need to fix those. But anyway, the validation that we added to this model, it does 2 things. It makes sure that the output of GoldSim matches the output of another tool. The other tool that we looked at is called the e-water rainfall-runoff library toolkit. And this is a tool developed in Australia. You can get the installer from their e-water website. So if you just Google e-water and then RRL, you will find the tool that we have used to do this validation. So what we did is we took the same inputs, precip, time series, evapotranspiration time series, and then also the constant inputs that you saw on the dashboard. We put those into the RRL toolkit, ran the model, and then we ended up with a time series of runoff, in which we then copied and pasted into this model. And the time series is just embedded in GoldSim. We just copied and pasted those values, and they are daily values, by the way. And we put those into the model, and then we compare our calculated runoff to that tool to make sure that we don't have a variation from that, to say, okay, this implementation is valid. The other thing we do is a mass balance check, just to make sure that the total inflow being precip and total outflow being evaporation losses and the runoff. Make sure that if you take the difference of those two, also with change in storage, that you get very close to zero, and we do. If you don't, then there's messaging. You get a warning when you run the model, so you'll be notified immediately that, hey, there's something wrong. So we added that to the model to provide some more confidence in this implementation. Okay, but the big change that we made that I want to talk about is not necessarily a change in the way that we conceptualize the model, but instead just the way that we handle working around the bounds of these stores that are in the model. Okay, so previously we had upper and lower bounds in our storage elements in GoldSim. So what do I mean by that? If you're familiar with the reservoir element in GoldSim or the pool element, you'll know that there are ways to set the bounds in those, the lower bound and the upper bound, meaning that GoldSim will not allow storage in those elements to drop below the bound or go and rise above that bound. Instead, what happens is, as you approach the lower bound, when you hit it, anything that you are trying to withdraw from that store will be set to zero. You will no longer be able to remove. Actually, it's not set to zero. It will be reduced such that the lower bound is maintained, is what happens. But when you hit a bound on one of these stores, GoldSim will, by default, insert an unscheduled time step. And so what was happening here is that if you allow unscheduled events to occur in your model, that AWBM, because it has 3 different stores in there with bounds, mainly the surface stores, because there are bounds set, that the model could be generating unscheduled events when these bounds are hit, thus potentially impacting the rest of your model. So at the time, what we suggested was to just disable unscheduled events in your model, and then you won't have that problem, and that was fine. However, there are a few users out there that they want unscheduled events in their main model, but they just don't want AWBM to be impacted by them, nor do they want AWBM to instigate these unscheduled events. So we have removed the bounds from the store, mainly the surface stores part of the model, and explicitly calculate outflows to avoid going below or above our bounds. So we define our ET losses in such a way that as we approach zero, or our lower bound, then we just explicitly calculate a flow that avoids crossing that boundary. So that equation is shown here, where we say outflow explicitly finds lower bound. What I mean by that is we reduce our outflow, or our ET outflow request, by using a min function, in which we will usually try to ask for the ET amount from the time series, but we'll use a min function to make sure that we switch to just the total precip in plus the amount in storage at the moment. and take whatever is the minimum of those two. So sometimes as you start to approach the lower bound, as the surface store begins to approach zero moisture, then what we do is say, okay, we cannot take the ET. We don't have enough water, we don't have enough precip coming in today, and there's not enough current storage in the soil at the moment to provide you with this ET that you're requesting. So we just reduce it using this min function. It seems pretty straightforward, and it is. However, you can get to a point where there's some numerical error, so you could see very, very small, either negative or just above zero values. And I'm talking very small, in the order of 1 times 10 to the negative 16 or 1 times 10 to the positive 16, kind of floating around there, which I concluded that is fine to have. It does not impact anything significantly as far as the runoff is concerned. The way that the RRL tool works in this case is they allow a negative value. They allow the ET to be removed and calculate a negative surface store value, but at that point in time, they just replace it with zero. So they might calculate a negative and then just replace it immediately with zero. What I'm doing is, for all intents and purposes, the same situation. Okay, so now on the upper bound, this is where we calculate overflow from the surface stores. We calculate that also explicitly by anticipating, as we approach the upper bound, we anticipate hitting the upper bound by just simply doing a quick comparison between the current value of storage and its capacity. So by subtracting the two, we can find out how much is remaining before we hit the upper bound and take that into consideration. So that's how we can calculate the overflow. And once we do that, we ensure that the store does not exceed its capacity. Okay, so that is really the big part. That's the change that we've made. Instead of just having GoldSim figure out where those bounds are and when we hit them and what to do about it, we have to do it now in these equations. Okay, so that's what we do. Now I want to show you the model and those equations. Going up to the top. So this is what the top level of the model looks like. Going back into edit mode, you can see here the precip and evaporation time series elements. And let me open those up because it's really important that you see how they are defined. So the precipitation data, in this case, is just locally defined, meaning we just copied and pasted it into this table, but you can load it from Excel or bring it from other places. And like I said, it does not have to be a time series. The model is just expecting values as we simulate through time. They don't even have to be changing values, but in this particular case, it's really important because we want to simulate a daily precipitation over time and calculate a resulting daily runoff from this. Okay, and because of that, it's very important that your time series is set to be represents constant value over the next interval. The reason for that is because if you set this instead to interpolated, then it's really important to understand what happens if you have an unscheduled time step. Let's say in your main model, for whatever reason, maybe you're simulating an earthquake that happens randomly, or you're simulating some other tailings facility or a reservoir or something that causes an unscheduled event to occur in which you have all your elements need to update again at a time other than your scheduled daily update. So if that occurs, and this is set to instantaneous interpolated, well, what that means is your precipitation value will now be different than what it was at the beginning of the time step, of the scheduled time step. And that can have an impact that's unexpected and different from what you might see in another tool like the RRL library tool, which does not ever insert any unscheduled events. Because GoldSim is a dynamic simulator, it allows you to insert events at any point in time. Therefore, you just need to be careful that this is accounted for correctly. So I would say if for time series, it's really important that you maintain constant values over the interval. Okay, same thing with evaporation, by the way. If we go into the model, then that's where all of the calculations are taking place. And you can see we have the surface stores here, and then we have the splitter that splits the flow to surface runoff and then base flow. And that's using this constant factor called the BFI, a calibration factor. We also have some time settings that are very important that you need to be aware of. Let me go in there. Mainly it's this DT. This stands for delta time, not to be confused with the time step length that's built into GoldSim. This is also very important to understand. If you right-click in the browser here, click on Show Element Subitems, then you will see all of GoldSim's run properties. They are called local properties here. And if you expand the simulation folder, you will see there's a time step length output. This is the amount of time since the last update. This is not a value you should be referring to when you want to calculate things in the AWBM model, such as a flow rate as a function of the storage. You definitely want to use a constant, especially in the case in how we are using the value. It needs to be a constant. So in our case, we're simulating 1 day time steps. And so it has a constant value of 1 day. Okay, so if I go, these other elements will be removed shortly. They were just there for some testing that I was doing. Okay, so we're using a value of 1 day, and we can see what that impacts. You can see that the output port of DT has an indicator that it's being used elsewhere. If I right-click on the element and select Effects, we can see what it's affecting. It's affecting the discharge rate, which is a recession rate for the base flow. It's being used as a recession rate for surface runoff stores. And it's also being used for the evapotranspiration losses in the surface stores. So let's go there first. So now we are in the surface stores. If I go up 1 level, up, we are here going into the surface stores into here. Okay, so what we have here is the amount. This is the store, the amount in store, and this is a vector of surface stores. We have an initial value, which is the initial surface store value entered on the dashboard as a percent multiplied by the 3 capacities. So right now, right now we're saying that the initial surface store is 0% multiplied by the capacities. So if you said 50%, it would cut all these in half as the starting value. The inflow coming into the surface stores is the precipitation, which is divided up and allocated based on the 3 areas. So if I look at P, that's the precipitation multiplied by those 3 proportion values, A1, A2, and A3. So it lands into the 3 different buckets. And then we withdraw from the 3 different buckets our ET losses and any overflows should they occur. So the real important part here is how we calculate the ET loss and the overflow. ET losses is calculated as a function of the amount that's currently in storage. If it happens to be less than the evapotranspiration amount that we're asking for. So that's the potential ET. That's why it's PET, potential ET. So we take the minimum of what we're asking for, or the precip coming in plus the amount divided by dt. So the amount divided by 1 day in our case. So you can see that if you changed this model to an hourly time step, dt would have to be changed as well, because you're making the assumption that we are operating on a 1 hour time step with our inflows or our precip values. Okay, then our overflow is, we do a similar thing, except on the upper end. We say here that we want to anticipate when we might hit the upper bound. And so in this case, we are looking at the current amount, subtracting the capacity from that and saying, okay, if we are below the capacity, then this will be a negative number. Therefore, that will reduce our overflow. However, instead, if we determine that the amount is that we've updated to is greater than the capacity, in other words, we're above the limit, then it will add to the net inflow, and our overflow will then be increased in order to bring the water level or the amount of moisture back down to or below the capacity. Okay, that's how the surface stores work. If I go, and then you see that overflow is calculated, and then we take the sum of the overflows, which is just taking the sum of the vector, and then that's brought into the splitter in which we split the flows to the surface and the base flow runoff. Okay, so let's talk about how this model runs. What I want to do first is show the simplest case in which we have no inserted unscheduled time steps. If I go to the simulation settings of this model, what we used to tell you was that it was very important that you uncheck the box here to allow unscheduled updates. And that just made sure that we had no unscheduled updates, and that when we run the model, we get exactly the same result as in the other tool. And that's what happens now because I am not inserting any unscheduled time steps. If I go to the model verification folder and then I look at our calculated runoff compared to the RRL toolkit, you will see that the values are right on top of each other. That's the red and the blue. I added a small symbol to the blue so that you can see them on top of each other. We could look at the table values. You can see that GoldSim and RRL, the two I've highlighted here, are essentially the same. I am showing a higher precision here, but you can change that by holding the Alt key on your keyboard and then typing the left arrow key. So if I reduce the number, you can see they're close together. Our error between these two, I calculate that over here. And so you can see our error is very small. We're talking about millimeters here. So I would say this is within definitely not anything to worry about here. So on a 1 day time step with no unscheduled events occurring, we have an exact match to the other tool. So that's good. That builds confidence in what we're doing in GoldSim here. We also have a mass balance check that looks to make sure that the total inflows minus outflows minus change in storage equals 0. And so this plot should show you 0, and it's very close to 0, as you can see here. Okay, so we're good with that. The next thing we want to do is look at what happens if you insert unscheduled time steps. Okay, so I'm going back to the simulation settings. If we look at our advanced settings here, we are allowing unscheduled events, and in addition to that, we are temporarily including unscheduled updates in our time history results. So when we look at a plot, we can see everything that's happening. Now this is a temporary setting. I do plan to turn this off before I ship this model to our library so that you guys can have this, and this box will not be checked. When you check this box, it really should just be done temporarily to better understand the model, doing some troubleshooting. And then when you're ready to go into production mode, you should uncheck this box, because there are certain types of histories that will not be shown in high resolution. It's really just to show scalar outputs of time histories in high resolution. Typically, it's not something that's needed to be shown every time you open a chart. So, okay. So now that we understand that unscheduled time steps can occur in our model, let's go ahead and put some some random time points in the model to simulate what might happen if you put this model into a larger model that has unscheduled updates. Okay, so I'm doing that with a timed event with an occurrence type of random time intervals. So randomly, we're going to insert events that are on average happening once per day, but are random. And so this causes a whole bunch of unscheduled time steps to be added to the model. Okay, so I run it. And then if we go back and we look at our validation plot, you can see that the error is a little bit higher. It's 0.6 millimeters. So there were some small differences, and let's zoom in on one of those. So I'm holding down the control key, and then I'm drawing a rectangle so that we can zoom. Okay, and so here you see the difference. There's this small difference between what GoldSim simulates and what the RRL toolkit found. But there's something that's very important to understand here. Okay, the RRL toolkit output was only generating outputs on a daily time step. So it's not a real fair comparison here. GoldSim is recalculating all of its store values at an unscheduled time point. I'm going to zoom just a little bit more so we can see what I'm talking about. So we have this time point that I'm pointing at right here that's unscheduled. This is an unscheduled event, and GoldSim is being requested to calculate or re-update all of its store values and its outflows at this unscheduled point in time. Well, what that means is it's calculating outflows based on a new store value, not a value that happened at the scheduled time point here at midnight. So that will cause a slight variation, and you could even consider it as being more accurate potentially, because it's calculating a flow based on an updated store value that is closer to what it would be if it was if this was in reality as we're going through time here. So the RRL toolkit never had that chance to update any of its values in between these time points of one day. And so it's just doing a straight linear interpolation of a time series. That's all that we're doing with this blue line, is just a linear interpolation between two values. Whereas with the way GoldSim works, it's updating the actual model at a new point in time. Therefore, we will see slight variations. But even if we run this model for a long period of time, which I will do now, we shouldn't see major differences. So I'm going to run the model through the entire historic record that we have in our time series and see where we end up. We still didn't get any warnings, by the way, when I ran the model. That's a good sign, because both of these error checks are set up to issue a warning if we exceed the tolerances. Okay, so here we are looking at all of these years. You can see that we still have not exceeded 1 millimeter of difference between the two tools. We could zoom in at any point here. For some reason, reset the scale. Let me look at our scales. So if you want to adjust the y-axis, y2 axis, x-axis, you can do that manually through the chart style by clicking on these axis tabs here. And you can see that the y-axis is not set up to auto. If I change this to auto and apply it, well, it turns out it's pretty much the same, but before I think it was set to 30, so it was truncated. Anyway, if you zoom in here, then you will see an area in which we have some differences right in here. But they're still, like I said, fairly minor differences. Still probably within an acceptable range if you want to allow unscheduled events. If you want to produce exactly the same results as the other tool, it is possible. And I do have an implementation that what it does is it just generates, before the model even walks through time at all, we have a submodel that generates an array that is essentially the output that our RL toolkit generates, and only those values. It only generates the values for scheduled updates and nothing else. And then as you walk through time, it just does linear interpolation like we do on RRL. But this is a tool that it's built to give you exactly the same answer, but is not as dynamic and easy to incorporate. Is not as easy to incorporate it into your model. But if you are interested in an implementation that produces exactly the same values, then let me know, and we can provide it. But as far as this goes, it's so far with the testing that we've done, it appears that this one is acceptable, and we definitely have a reason. We know why there are these very slight deviations from the RRL toolkit, and that is that GoldSim is updating its store values and therefore outflows as it inserts additional time points, causing slight differences between these flows. Okay, so next topic, to cover just again the limitations of the model. It's really important that you make sure that your climate time series, precip and ET, make sure that they are constant over the next interval. Make sure that you know whether or not you are inserting unscheduled time steps or not in your model, and the potential implication of doing so. So just also keep in mind that GoldSim updates its outflows based on the current store value at any point in time, even if it's an unscheduled update. That is different than the way most hydrologic tools, software tools out there work. Typically, they have a scheduled time point and nothing more. So that is going to be a difference. It's also possible that you will see very small store values in the surface stores just from numerical error, but should not impact your final results. Okay, and finally, what's next with AWBM? Well, we have seen that this model can be used outside of Australia quite successfully, especially in arid regions. But I would be curious to know, if you decide to use it outside of Australia, how it works for you. If you have problems, I would be interested to know. But so far, I have seen many people use it in Canada and the US. I don't know about South America, and I'm not sure about Europe and Africa, but it has been used in the US and Canada with success. One thing I want to do with this model is improve the calibration functionality. There are a couple of tools that we can implement that are documented in the original Boughton. Boughton is the author of this tool originally, and in their documentation, they talk about ways of calibrating. And one of those is to look at monthly total precip and compare that to monthly total outflow runoff, and it can give you a good idea of what to set your surface storage capacities to. So we might be able to add something like that to guide you on what you should put your capacities at. It's always it's recommended that you first adjust your surface storage capacities, the C1, C2, and C3, that you first adjust those and then move to your uh, surface runoff and base flow runoff uh, parameters as the second step in calibration. So the idea is that we add some functionality to the model to assist with this calibration, and then maybe look at linking it up to a stochastic weather generator and demonstrate its usage in larger models. So that these are the things we'll probably be looking at this year, presenting webinars on. Okay, so that looks like we're about out of time. That concludes the presentation. I appreciate all of you joining, and hopefully you can join us next month. By the way, we do have a guest speaker next month, so it should be quite interesting for many of you. And so do stay tuned. If you are not on our email list, being notified about these webinars, please let me know, and we can add you to the list so that you're notified each month before these webinars occur. So thanks again for joining, and please let me know if you have any questions. I'll wait around a bit for that.